And it's great to be here and talk about our most recent work, where we address the novel problem of intermittent-aware neural architecture search to automatically find deep neural networks that can intermittently execute on lightweight devices via ambient power. So energy harvesting is a sustainable and low-cost solution for edge IoT devices. However, as ambient energy is weak and unstable, they experience intermittent power with frequent power failures. And at the same time, the advancements in deep neural networks have pushed inference to the very edge. And recent research have even enabled intermittent execution of deep neural network inference across multiple power cycles. As deep neural networks have an intractable design space, the process of DNN design is typically automated using neural architecture search techniques. So therefore, the intermittent-aware neural architecture search is a novel and crucial problem to solve to support intelligent and batteryless edge devices. On a resource-constrained system, DNN layers are processed as tiles. And to compute a tile, the required input data, the tile input data, is fetched from the non-volatile memory to volatile memory. And the computed tile output is written back to non-volatile memory. To improve the inference performance, tile input data is fetched once and generally reused across subsequent tiles of a layer. On an intermittent system, intermittent systems execute using the harvested ambient energy in an energy buffer, such as a small capacitor. This essentially defines the energy budget of a power cycle. And upon power failure, the volatile data and the state of the system is lost. So progress preservation is typically performed during inference, where progress indicators are backed onto NVM, along with intermediate computation outputs. And upon power resumption, progress recovery is performed, where the preserved progress indicators are used to refetch the required input data and resume the interrupted inference progress. Typically, a batch of intermediate computation outputs are preserved with a single progress indicator to reduce the overhead of progress preservation. So we present a key finding regarding the unsuitability of DNN solutions found by existing neural architecture search frameworks for intermittent systems. We observe that NAS primarily maximizes data reuse to improve inference latency without being aware of intermittent execution behavior. And so, as NAS does not consider the key costs or design spaces related to intermittent inference, it may find inefficient solutions which may violate the end-to-end inference latency requirement. And even more seriously, maximizing data reuse may lead to large and energy expensive solutions, which may be unsafe as they may exceed the power cycle energy budget of an intermittent system. And so we present a general principle. To generate and deploy neural networks on intermittent systems, an intermittent-aware neural architecture search should find the right balance between data reuse and the costs related to progress preservation and recovery, while ensuring the power cycle energy budget is not exceeded. And following this general principle, we develop INAS, the first intermittent-aware NAS framework to find DNNs that can be safely and efficiently executed under intermittent power. However, introducing intermittent execution behavior into NAS raises two key design challenges. The first is how to define a feasible solution space which considers intermittent execution behavior. This is particularly difficult as the design parameters and energy budget related to intermittent execution are tightly coupled with conventional execution design parameters, as well as hardware and latency constraints. The second challenge is how to analytically formulate the performance of an intermittent execution design solution. This is non-trivial as the additional key costs related to progress preservation and recovery have to be accurately captured. So we address the first challenge by introducing an intermittent-aware execution design explorer that introduces a preservation design space and a power cycle energy budget constraint to NAS. The preservation design space includes the batch size of intermediate computation outputs preserved together, and it is unified and jointly explored with the execution design space. The power cycle energy budget is enforced together with the hardware and latency constraints during design space exploration. And we address the second challenge by introducing an intermittent-aware abstract performance model, which formulates the additional costs of progress preservation and progress recovery, as well as computation, for a given candidate intermittent execution design. This allows us to formulate the energy and latency costs of a power cycle, which in turn is used to derive the end-to-end inference latency across multiple power cycles. To evaluate the improvement brought by INAS to an existing hardware-aware NAS framework, we deploy the solutions derived by both frameworks on a lightweight Texas Instruments-based device powered intermittently. And we evaluate under 3 different data sets that represent typical TinyML applications. We also conduct experiments under different capacitor sizes and different inference latency requirements to further evaluate the ability of the frameworks to find feasible solutions for different intermittent execution and application scenarios, respectively. And compared to the hardware-aware NAS solutions that can safely complete inference, the INAS solutions reduce the end-to-end inference latency by 60% on average. And we observe that improvements are more apparent when it is more difficult for hardware-aware NAS to find feasible solutions, such as under a small energy budget or under a high latency requirement condition, where complex networks are found by hardware-aware NAS. So by design, INAS does not degrade or improve accuracy. So the solution accuracy is comparable to hardware-aware NAS solutions. INAS incurs an average of 7% higher search overhead compared to hardware-aware NAS to explore an additional design space and calculate the inference latency across multiple power cycles. So here we present a demo video that compares solutions found by INAS against a conventional hardware-aware NAS under intermittent power. The intermittent system here executes an image classification DNN inference using only the harvested energy from the lamp. And runtime information is displayed on the user interface, including the inference progress and status of the power supply. When the energy budget is small, the hardware-aware NAS solutions may become unsafe and unable to complete the inference, while INAS ensures the derived solutions can always safely make forward progress. When energy budget is sufficiently large, hardware-aware NAS solutions may be inefficient and require a large number of power cycles to complete the inference. In contrast, INAS considers intermittent execution-related costs as well as a preservation design space, so the derived solutions always meets the end-to-end latency requirement. It's also worth mentioning that INAS is an initial attempt at introducing intermittent execution behavior into NAS. And we hope this work will motivate a rich body of potential extensions in the future. For example, model compression techniques such as hardware-aware pruning and quantization-aware training can be integrated into INAS to further reduce the inference latency of the solutions. As well as INAS can also be extended to consider runtime inference adaptation techniques that balance performance with a minimum amount of accuracy degradation, such as early termination based on multi-exit networks. And to improve the search efficiency, recent NAS speed-up schemes, such as differentiable search strategies or search space reduction techniques or concepts such as weight sharing can be also applied to INAS. So it's also worth mentioning that our research group is actively working on enabling batteryless IoT devices to intermittently execute DNNs via ambient power. Most notably, our runtime middleware stack, referred to as Hawaii, enables hardware-accelerated intermittent DNN inference to be accumulatively executed across power cycles. And our INAS framework automatically finds intermittently executable DNN models. Both Hawaii and INAS received the Best Paper Awards, respectively, for 2 years in a row at CODES ISSS 2020 and 2021. And to conclude, we present the first work to introduce this novel problem of intermittent-aware neural architecture search. This problem arises due to the unsuitability of existing NAS for intermittent systems that cannot be solved via straightforward extensions to existing NAS approaches. And we provide a general principle where to find safe and efficient DNNs for intermittent systems, which is followed during the development of INAS. We address the design challenges of finding a feasible solution space by introducing an intermittent-aware execution design explorer. And we address the challenge of formulating the performance of an intermittent execution design by introducing an intermittent-aware abstract performance model. We show that INAS solutions reduce the intermittent inference latency by 16 to 87% while achieving comparable accuracy. And improvements are more evident under a small energy budget or when hardware-aware NAS finds complex network architectures. And lastly, our INAS framework is made open source, and this enables anyone interested to design and deploy DNNs on energy harvesting edge devices. And thank you for listening, and I'm happy to answer any questions regarding our work. And please feel free to contact us for more details that you may require. Thank you.
Okay, thank you for the very exciting talk and the very excellent demo, because this is the first work I have seen that for live work on the intelligent network architecture search on the intermittent systems. It's really a very smart solution. So is there any question that you can post your question on the chat box? Maybe I can ask the first question is that, is the proposed INAS also suitable for other neural networks, such as the graphical neural networks or other reinforcement learning, etc.? Yeah.
Yeah, so at the moment, we currently primarily support convolutional networks and slight variations where you can convert different networks into convolutional networks, such as RNNs. We have not considered graph neural networks, but the fundamental methodology can be applied where you first have to analyze the inference system and determine what the progress preservation and recovery costs are, and then plug them into the framework, and then INAS can find suitable solutions.